Good afternoon to all. It's a pleasure to me participate in this course in the third edition. I think you are lucky because the course is really interesting, and we will talk today about the Meteosian data set. Okay, we analyze the climate analysis, forecast, and institute data, the terminology. Widely used in marine data. I am Tomás Fernández. I come from the University of Cádiz. I am marine scientific of the University of Cádiz. Basically, the content of this 1 hour that we have, we will see the different types of Meteosian data and the main characteristics. We will define the analysis, reanalysis, and the climatology. We will provide some overview of some of these data sets that are publicly available and you can download and use for your application. And we will see specifically in a bit deeper some details of the cement product relative to the physics data set and also to the in situ, okay? And we will see also some lexicon about the quality information and product user manual of this specifically dedicated product of cement. Okay, it's important, this lexicon we will float in during all the talk because it's important to establish, let's say, a common language that allows us to understand how the data are stored, what the data contain, etc. So we need to talk same language that the people that work with the data talks. Okay, this is important to access efficiently and use efficiently the data. Well, this is a snapshot of the Ocean Observatory System report card in 2021. What you can see here is the dot of data acquisition or path by glider, by boat cruise, etc. And this is in situ measurement. Besides, we have the remote sensing like satellites or land shore remote sensing data sets. So as you can see, actually there is it's a quite complete wide coverage of this kind of the data in marine data. This is not always like that. I mean, in previous decades, previous years, we have some gaps in some areas we will see later, and the data are not evenly distributed. Okay, the observed data are not evenly distributed around the globe or on all the seas. In general, we look for long time series of data. This is one of the main characteristics that we need. Okay, long time series. Long because if the time series is long enough, we can do statistical analysis. We can do statistical processing to get or to produce important information. We will need this long and reliable record for study the climate change. Clearly, we need a long time series for the monitor the ocean health, for forecast and to provide forecast and warning, for instance, for the extreme events that hit the coast, like hurricane, etc., or for to study which are the trend of temperature, which are the trend of sea levels in the ocean, that you know is actually one of the main challenges that we have to face as society. So we will try to classify the data. Well, first of all, Meteosian. what this word means. In general, meta-ocean is used for the data regarding the meteorological data or the data regarding the ocean, okay, the seas. So we can classify this data mainly in two main groups. We have numerical data that come from numerical model, or what we call it data assimilation, which is the data that come from numerical model but corrected with observation. The first group, numerical model, it doesn't mean that we don't use in situ data. Okay, we need in situ data to fit the numerical model. To use the open boundary condition, we use the in situ observation and measurement to calibrate and to validate the model, so to assess the performance of the model and to improve the performance of this model. Okay, this is important. This is important to understand that even if we talk about numerical model group, indirectly we are using observed data. Okay, so inside of this group numerical model, we can talk about hindcast. When we produce time series from the past, we talk about node casting. When we analyze we provide data for the present, short present, or we talk about forecasting when we produce data for the near future. Okay. Then in the second group, we talk about data simulation data. What that means? It means that the outputs of the numerical model are corrected by observation. Okay, we use the observation to correct the product of the numerical model to fit, to improve the results of these numerical models. Okay, that way we can talk, if we analyze the past, about reanalysis. Okay, or we can talk about analysis if we focus on the present. The main idea is that with the observation, you can modify the output of the numerical model to this data simulation. Okay, with the most recent observation. Now, this meta-ocean data can be classified according to the level of processing. In this regard, we have five levels. Okay, we have level 0, where we talk about unprocessed instrument raw data, usually the units of the digital number, and at the instrument space and time resolution. Okay, all available supplementary information need to be appended. All this information that need to be used for this processing of this data. Then, when we transform this digital number on sensor units, for instance, brightness, temperature, radiance, or backscatter radius, we pass from level 0 to level 1. Okay, again, all the information needed for post-processing should be appended to this information. Level 1 of the product can be already geolocated. Okay, then when we transform these sensor units to geophysical quantities of interest, wave height, cloud fraction, aerosol, optical depth, whatever, we talk about level 2. Okay, we talk about level 2. And this level 2 have associated and uncertainty estimates. This is also important. When we transform, interpolate spatially or temporal, we make an example that allow us to get gridded product, we talk about level 3. And when we use data like climate index or analysis of multi-lower level product, we talk about level 4, okay? We need this level 4 is also gridded, and usually they have also an uncertainty estimation of the sample data, okay? So these are the 5 groups. So we'll talk about the reanalysis and analysis products. An analysis is a snapshot of the state of the ocean at a given time, and it is done or produced using a model, data, and observation, both, okay, both, to provide the best fits produced on the fly. When we talk about an oceanographic analysis, we talk about data that come from the model, that modeling the state of the ocean over a long period of time, so several years, it's not just the present, it's several years, but correcting with the best available past observation, okay? And we introduce here this scheme where we introduce the quality control. All the data that we use, I mean, observed data should be quality controlled to don't ruin our data. This is a really important step. Okay, so basically we have the input observation, we control the data, we adjust or statistically correct the model forecast or the model output with this quality control observation, and we produce these fields of different variables or parameters to be analyzed and to get important or relevant information. Now, when we talk about the analysis data, we are talking about data that have a longer time series because as we already stated, we need longer time series, but which is important in this case. First, we have 3 or 2 components: the global observing system, okay, and the reanalysis, in case we are talking about global, the model, and we have the interaction between both, which is the data assimilation. What is important? All these both component of the system and the processing, the data assimilation itself should be consistent during the whole period. I mean, we cannot change or the way how we assimilate the data. We cannot change the way how we make the numerical simulation, or we cannot change the way how we processing the in situ measurement of the satellite data. Okay, this is important because otherwise the information that we can retrieve, like in this case, the trends, can be fake because it can be due to this change in the processing, not to the change in the reality. Okay, this is an important thing. But we can see here, but we can produce with this kind of system is mapped without gaps, in the sense that we have a long time series covering the whole globe, because we use numerical model. We assimilate the data for several decades. So we can produce and study the climatology, we can study the trends. Here you can see the temperature anomaly in the first, from the 80s to 89, 95, 2004, and 2010, 2019, okay? And you can see an increase in the sea surface temperature. To be sure that these results are meaningful, remember that we should keep consistent all this processing, always constant during the whole period. Okay? But life is hard. Not all, no, I mean, all these analyses are not perfect. They are, or they have associated uncertainty. And what you can see here is the comparison of 3 data sets. National Center for Environmental Projection and Climate Research Unit. And the third one would come from the European Center for Medium Weather Forecast. Okay. So now here you have the climatology, seasonal climatology, and the annual mean. Let's have a look just to the annual mean, and you will see when the difference or the bias between both data sets are -1 and 1 in this range. We have gray, we have 0 in this white, but we have some important bias in this annual mean, like 3 here in Siberia, which becomes even larger during the winter. You see 7 degrees. So, and these bias, as you can see, are not constant in space. This is really important to know. I mean, we will have this publicly available information data set that is a powerful weapon. I mean, we can use to deliver very important result, but we should be aware about the limitation of each specific data set that we use. Okay, this is important to.
Sorry, sorry for interruptions. And dear Thomas, and first thank you for the lectures, but I think your internet is not that good enough, and that's why maybe you can close your camera, and then because voice sometimes stop and then we start again. I mean, it is not good quality enough the voice because of your unquality internet. I think maybe you can close your camera, then we will be more quality hear you.
Oh yeah, but is my problem or Kadir? Sorry, Kadir, is Audrey, you can hear me well, or is
I hear you, but sometimes voice get interruptions. It freezes, you know.
Yeah, but I'm asking.
From my end, I can hear you well.
So this is the problem, Kadir, that maybe it's your connection. That I mean, if the others are okay, we will continue like that because it's not a problem of mine. I mean.
Anyone else can not hear? Is having problems?
Hello. For me, it works fine.
Okay.
So it seems like maybe it's your connection, Kadir. If
okay.
let me know again. Okay.
Okay.
Sorry. Okay. Now there is I mean, very useful web page, which is this GWIT, which is standard for web basic analysis intercomparison tool from the NOAA, where you can use this kind of tools to compare different data sets. Here you have the difference between GODAS and SODA3, 2 different data sets. In the sea, I mean, in the surface temperature, so 5 meter potential temperature, surface temperature. And what you can see here is how this bias is not homogeneous on all the space we have in the southern ocean, an important bias, right, to 3 kelvins. But also we have an important bias in very complex areas like the continental current, Kuroshio, or the Gulf Stream current. Okay, this is the kind of information that we can retrieve from these tools, which is quite useful as I said. So clearly, the analysis data are improving. I mean, nowadays we are powerful computing service. We have important resources. to dedicate it to this purpose. We have evolving science and how to evolve, and we have a very say precise or accurate analysis of data set. You can see here a comparison between the both data set for the same event. This is the Florence hurricane here in the west coast of United States. Take place in September of 2008, and we compare in the left panel. You are seeing the ERA 5 analysis. It is one of the latest of the European Center for the weather forecast. And on the right, we have the previous one, which is ERA interim. Here in the table, you can see the difference between the data sets, both data sets, and this is the main characteristics that we will find in all the data set that we when we look in a data set. We have basically the resolution, horizontal resolution, atmospheric, horizontal resolution, vertical resolution, temporal resolution, the period of coverage, and you can see that ERA 5 have increased the resolution more than twice, so it's 31 kilometers instead of 80, almost 80 kilometers, but have the previous ERA interim. So what you can see here is how we can capture better the phenomena. This is the color, I mean the isoline of the pressure, surface pressure, and the color is the accumulated rainfall associated to this pressure perturbation. Okay, so especially for extreme event, it's important because the scale of these phenomena are lower. It's important to get higher resolution, and you can see how the accumulated rainfall, I mean, it's arrived to 300 millimeters, and here it's arrived to 700 millimeters with this ERA 5. So this is the different in power, but we should be aware about the implication. In the same table, you have below the resource requirement, CPU to produce the data, and for instance, the disk storage in gigabytes. We need an important hard drive, so we have 450 gigabytes. We need to storage ERA 5. Instead, for ERA interim, it's enough 6 gigabytes. So just to compare, usually when we have a very detailed high resolution, we need more, and to produce it, we need more CPU, clearly, and we need much more storage. Okay, usually high resolution are restricted to not to lower in general. In this case, is lower, and its resolution is spatial or temporal. Okay, it's an important difference. Also, the temporal resolution, where we have here in ERA 5 we have hourly, and we have 6 hourly. So for the peaks of an extreme event, it's important really also to have a very high temporal resolution. But now we are talking in general about climatology data, but we have not defined this climatology. So we need to define this. I mean, there is in general there are a lot of definition, but in general, what we should understand for climatology is a long time series in general. 3 decades or more, several continuous decades, to construct this statistical ensemble. Okay, we can define the climate normals according to the World Meteorological Organization, like a period average computed for a uniform and relatively long period comprising at least 3 decades. We need these 3 decades because we can have interdecadal variation, and this climate normal should not be or cannot be affected by this interdecadal variation. Okay, but in that way we can consider the climatology in terms of average. Okay, and see the difference in the global temperature, for instance. But what's another important is not only the average for climatology, it's also important the variation. What you can see here is how the variation is higher in the southern, so in the northern, I mean the high latitudes, and in the continental. This is a standard deviation of the surface temperature on the continental, and it's lower in the ocean because the ocean acts as a buffer that smooth, okay, this variation. But also, if we have a long time series, we can compute the percentiles, and we can use like a threshold, and we can study the stream, considering a stream of everything that over this threshold. Okay. Let's to talk about some reanalysis of the different data set. We have one, this national, this comes from the National Center for Environmental Protection. Here you can see the characteristics, again, resolution. This case is 2.5 degrees, which is, I must say, not so detailed for the global, but anyway, it's a good analysis. We have temporal coverage 4 times daily, so it means that we have 4 data, so it's 6 hours. We have daily and monthly average. Okay, the coverage is global. The levels that we have 28 sigma level of 17 pressure level. Okay, this is one of the analysis. You can access this analysis download and use it. It's come from the NOAA, which we should recognize that it's one of the first organization that make available, publicly available, this kind of the analysis in the past. Okay, now you can see the data for another different analysis, like the World Ocean Atlas in 2009. In this case, it's not data from global, from numerical modeling. These are data that come from observation. Okay, these observations are gridded, so it's a level of product that we talked before, and we can have different climatological fields like in situ temperature, salinity, solvent oxygen, etc., etc. So it's also include associated statistical field, this oceanographic profile, and both in 1 degree Celsius or 5 degrees grid. Okay, this is pretty much the same, but like an update of this World Ocean Atlas in 2008. Clearly, we have improved the data and increased the data that we included this kind of atlas, just to show the evolution, of this kind of World Ocean Atlas. We have here in this table, okay, the different version from the first one in the 70s to the latest one in this World Ocean Atlas or database 2018, and we have here the different in situ measurement that compose this data set. We have conductivity, temperature, depth, mechanical fatigue thermographer, extendable fatigue thermographer, radar, drifting buoys, moving buoys, etc. So, but what I would like to remark is the increasing in number of total casts. You see this row, and how, for instance, in 2009 is 9 million casts globally, and the latest version of the World Ocean Atlas arrived almost to 16 millions of casts. Okay, this is almost double, and this gives you an idea of how we are progressing, how these kind of data are evolving in time. So it means it is a limitation, because when we try to extract some long time series, we miss some of this, okay, at the beginning, and the time series are shorter in this case, okay. But beyond this temporal limitation of this kind of data set, we have also important limitation, which is the spatially the homogeneity in the space. Here you have the cast per degree. I mean, in this grid of 1 by 1 degree, the number of casts that we have here, you have the scale of the color scale, okay, more than 20 is the red, between 2 and 5, and white, which means that we don't have. So in the 19th century, at the beginning of the 19th century, we have, sorry, the 20th century, we have, okay, a good coverage in the ocean, in the Atlantic, around Europe, northern hemisphere, world, but we don't have measurement on the Pacific. I mean, the Pacific remains unsurveyed for that period. Instead, we look to the first decades of the last century, 21st century. We have a much more homogeneous distribution of this information. Okay, this is one limitation that we should aware. Well, let's move a bit ahead, and you can see another reanalysis. I mean, we have just I want to show you some different analysis and what is the kind of information or useful information that you can get from this analysis. This is only, I mean, each analysis have a lot of variables, and depend on your interest. Maybe you are a biologist, marine, or you are more interested in the physics, but important thing is that you know where you can find the data, and according to your preference, your topic, etc., look to this specific data. Okay, so this is the GODAS, which is the Global Ocean Data Simulation System. We talk about numerical model, but that have assimilated data or the analysis. The coverage of the climatology is constructed from 82 to 2004. The coverage goes from the 69 to the present. Okay, we have penta products. We mean that we have 5 measurements per day, or 5 measurements per 5 days. And the kind of information that you can see, or one of the example is this missing layer depth. Okay, in the panel, the top panel, what you can see is the missing layer depth. What means when the missing layer depth is lower, is the upwelling, showing an upwelling, or when the missing layer depth is higher, it's showing the bottom water depth formation. Okay, the areas where the water is the deep water are formed in the ocean, or the upwelling areas. So where we have important implication, as we will see later. More information that we can get from this kind of analysis, like GODAL. For instance, the tropical cyclone heat potential. You know what is the of the cyclone heat potential is the temperature integrated from the surface to the isotherm of the 26 degrees, and it is provided to deliver an estimation of the. I mean, it's in few words, it's referred to the quantity of the energy that the ocean can transfer to the atmosphere and this is used to evaluate the probability of typhoon. So this is for the 2021 as a snapshot for this 10th of October, showing which are the areas of the that probably or more likely we can form some hurricane. A different data set, the SODA, is the Simple Ocean Data Assimilation. Okay, it's come from it's have a resolution of 1/4 degrees, or horizontal resolution of 0.25 or 28 kilometers by the equator. It has 50 vertical level, upper layer at 10 meters. So the period and time resolution covered from 1871 to 2008. What kind of the data they have assimilated? You see that they have a World Ocean Database 2009. Okay, and the forcing for the wind stress and what kind of formula. So you already have been. I showed 2-3 data set, and you can see the information that you use to describe this data set as it's always the same. Resolution, spatial horizontal resolution, temporal resolution, vertical resolution or vertical levels, coverage, etc. Why this are the main parameters? Because these parameters are the one that we should check before use a data set. In other words, the phenomena that we want to study have a spatial scale and temporal scale. We should get a data set that allow us to study this phenomena. To do so, we need to be sure that this data set have enough resolution, spatial resolution or temporal resolution. Okay, this is an important point. The picture that you can see here is the sea surface temperature in the west coast of Africa. So there is this point with lower temperature, which is showing us the upwelling areas. We talked before about the upwelling. As you know, I mean, the primary production on the ocean is limited by the content of nutrients. Okay, basically, when we have light enough and nutrient enough, we can have primary production and then the trophic chain, etc., etc. So here in the upwelling areas are important for fishery because we have a high rate of primary production, and the production of the fishery is higher on this area. So it's important if we want to study this phenomena to get a data set that have enough resolution to do so. So this is a study of one of my colleagues of the University of Cadiz, so Vázquez et al. We have studied the phenomena of the upwelling in the front of the Canary Islands, in the African coast. And you can see here is a World Ocean Database 2008, so observation on the top. And here, three different data sets. We have GLORIS, which is a global reanalysis from cements. This is a regional model for the area, okay, regional is not covering all the globe, but because it's not coverage all the globe, we can increase the resolution on some specific area. That's why this have high resolution, and SODA, which is one of the other that we shared before. And now this is the depth, and what you can see here is that the ROM is getting the higher temperature. This is the January, the tour season, sorry, summer, June, July, and August, and December, January, and February. And what you can see here is that during the intensification of this sampling in the summer season, the ROM, I mean the regional model, capture a very lower temperature in surface, or lower than the glories and than the other analysis. And if we look to the observation, is what we can see in the observation. Okay, the other data sets cannot capture, cannot reproduce this kind of phenomena, because the resolution mainly of the phenomena because the resolution mainly, okay, and these phenomena are very close to the cause, and we need a very high resolution. So it is always important to understand the limitation of the data and the characteristics of the process that we want to study to select the proper data set. So let's move a bit further, because we are a bit delayed. We will show some data relative to or some specification relative to the cements product. Cements product will be used in the practical session, so I recommend that you go and register. So basically, this is a Copernicus service where we have 5 main services: atmosphere, marine, land, climate change, security, and emergency. Emergency is quite variable. It have information for flooding, volcanology, earthquake, fire, I mean, different coastal flooding, river flooding, so different kind of emergencies. And we will focus on marine, obviously, so obviously in the ocean data. How they are organized. So basically, they have the data organized in 7 domains, 1 global, and 6 regional domains for each season, for each sea or oceanographic region: Mediterranean, Baltic, Northwest, EV area, which is Iberian, Biscay, Southern Ocean, here, etc. So it's an operational European service by European experts to offer the best information on marine modeling. I mean, it's a very powerful tool, very precise and very accurate data and data set. And I would recommend you to go there, register, please, if you are not yet registered. And play a bit with the information that we have, because we will use later in the practical, during the practical sessions. Okay, it's quite easy to register. You just go enter your data and go. We have this is more or less how it looks like. We have a corner. User corner with you have a lot of information about the webinar with the help center. We have a very useful help desk also. You can ask questions, they answer relatively fast and properly, so it's a good very good platform where you can find everything or almost everything about the ocean data, especially for our region, for Europe, but also there is so many products for global, global. Okay, how the catalog looks like. Okay, basically We can search in the catalog because, as you can imagine, the information that there is here in cements is, and specifically in this marine service, is big. I mean, it's quite a lot. So we need to be, we need to knock in the proper door, and this is more or less what we try to explain also today about of the language. But as I say, is really important. So we have the searching catalog. We have the parameter. We have the period. We have the area, and we have the keyword that we can use. So keyword, domain, time periods, and parameter. These are the main classes that we can use. Then how they are organized also inside of this different region or oceanographic areas that we talked before. We have first the product. This is the first level. Okay. For each specific region, oceanographic region, Baltic or whatever, we have different products. Inside of this product, in a second level, we have data sets. So each product can contain different data sets. Inside of each of these data sets, we have different parameters. Current velocity, sea surface temperature, salinity, dissolved oxygen. Okay, depend on what we are looking for or what we are interested. The resolution and the coverage are limited by computing power, our storage and storage capacity. As I told you, there is a relationship between this resolution and coverage. Usually high resolution, lower coverage, and lower coverage, high resolution. Okay. Now, if you look now this slide, you will get crazy because you don't understand at the beginning nothing, maybe, but we can go in this case is for this specific product, for the global physics. What we have? So we have the code. We need to decode this information. Okay, and this is a standard for all the product and all the data set that we have in cement. Okay, you have basically the legend to understand this code or this acronym. Let's start first for the kind of data that we have. We can classify the data in model, satellites, in situ, or mixed satellite and in situ. And this is coded by color. So the blue is model, orange, red is in situ, green satellites, and the data set that contain both satellite and in situ merged, we have this kind of violet. Now we have more information. NRT stands from near real time. It means no casting and forecasting in the term that we use at the beginning of the presentation. MI, multi-year, is a stand from multi-years, and the slide is used to describe mainly the reanalysis. I mean, go far back in time. Okay, now we have parameters. Which kind of parameters we can find? The layings here. I mean, we have the we will see you. I will show you in the next slide. Temperature, bottom temperature, salinity, sea surface height, velocity component. Okay, these are the parameters. Horizontal and vertical resolution, temporal coverage, temporal resolution. Not all have of the parameter or all the kind of data are available for the full period. Okay. For instance, near real time are only storage for the last part of the I mean for the last year. But when we look into the multi-year, okay, the analysis we go back farther in time. to, for instance, for this case is 93. Okay, now temporal resolution, only instantaneous, daily, mean. Okay, we have information here. Times daily, weekly, twice daily, etc. So this is the update frequency. How often the data are updated. If the data, if the dataset contains assimilated data, and what kind of dataset are assimilated, in situ, satellites, etc. So, and the level, okay, the level of the product that we see, like level 4, for instance. So this is the acronym of the description of the acronyms. Okay, temperature, sea temperature, in sea ice concentration, for shake, oxygen, etc. For the wave parameters, with significant wave height, mean wave period, stroke drift, etc. So these playing are inside of the manual that we will see later inside of the product user manual. Now, if we select one of these products inside of the cement, like this global physics ocean, we have the characteristics here. So main characteristic, extension, resolution, and parameters that we have available. Okay. Important, we have the information, we have the documentation. Relative to the documentation, there is two main products that we will describe briefly the next slide. Product user manual, which is a very important document that contains all the information needed to proper use the data, and at the same level of relevance is the quality information document, which is a description of the accuracy of the performance of this product, a specific product. It contains an assessment of this of the performance of this product. Okay. Level of processing, this is L4 because it's a given product, etc. We have assimilated data, etc. Now, we enter in a product and we select one of the datasets. Remember that for each product, we can have different datasets. And inside of the dataset, we can see different parameters, different variables. This is one dataset, this is another. If we scroll on, we can see more. Okay. And this is the kind of information that we can get from the website. We can download the PNG, I mean, an image, a depth of file, a time series, make an animation, etc. But we can go even deeper. I mean, we can make a fast analysis with this kind of data. And we can get a transit. What you can see here is a transit in the side of Gibraltar, in the 36 degrees latitude, for a given date. And we can see the variation of the salinity. We can see the very salty waters in the Mediterranean, how this very salty water is flowing in the bottom from the Mediterranean to the Atlantic, how this is forming intermediated salty water in the Atlantic, and how the surface Atlantic water is entering in the Mediterranean. Okay, this is the kind of information that we can get, and we can get very fast. I mean, using this data set. But okay, let's talk a bit about these two important documents that are associated to each product. I mean, this is quite relevant. The product user manual, where you have usually a chain record at the beginning, when all the changes are traced. You can follow who is the responsible or which are the main, I mean, the main description of the change in this manual. So it means that the product and the manual are constantly updated. So it's a system that is it's a live system, and it is continuously evolving, and this allow to improve the service and to provide a better data set. This is basically the data of content, how you can download the file, which are the file and the file format and the nomenclature, etc., etc. So these are the main characteristics. Remember that one product can have several data sets, and each of these data sets contains several parameters. The other document is the quality information document, which contains, as I said before, the change record and contain important information about the performance and the quality of this data set. For instance, here you have the temperature, or it's a comparison, okay, for this global data set. A comparison, you have the bias, so the mean difference between the observed and the model for 1 year. And here the root mean square error for this observed and model. What you can see here is where we can really trust the model, or where the model or the data set, you have a higher uncertainty, have a higher error. And this is important if we have an objective in one specific site where the model have a higher error, or in another one. I mean, we should probably find a different data set if we are interested in some specific area that this data set have associated a larger bias or a larger error. Okay, that is always important. Know to be aware about the limitation. So this is for the part of the model. We look now in the CMS, have a specific website for the in situ data set, which is the thematic ensemble center. Okay, this thematic ensemble center is organized more or less the same in terms of oceanographic region, Baltic, Mediterranean, all the different oceanographic regions and global. So we can filter the data by domain, by platform, by parameter platform. We can only get the mooring buoys, the drifting buoys, the glider, or whatever we are interested. And we can download and view also the data. This is organized or is operating in a different way, in the sense that for each specific oceanographic region, there is a responsible organization to deliver the data, I mean, to produce this data. This is the same domain, as you remember, that we have seen previous code. Now we have two different data. We have near real-time products and reprocesses delayed mode product. We will see this kind of data. This is a scheme how this works. We have an international organization and provided through this system that acquires the data. There is a first step, which is an automatic quality control. After this quality control, or during this quality control, the data are flagged. So we can, the data come from a flag that say this data is good to be used, this data cannot be used, this data is potentially used, you make some correction, etc. We validate the product in a second step, and then finally the product are distributed. Okay. So each regional center have the data acquisition, automatic, product validation, and product distribution. So the two main steps, we have the step one, automatic near real-time quality product, and this is the flag that have been used for the product. So that associated to the product, to each product, to each parameter, we have this flag. Okay, we can have normally 0, which is no quality control was performed, which is not in this case. We have always good data, probably good data, or we can have one of this bad data, that are potentially you can use but should be corrected, etc. So this is the first automatic quality control that provide near real-time products. Then in the light mode, there is a reprocesses of this data that produce this the light data, which is the visual quality control comparison to the or use I mean more advanced processing of the data comparison to a reference climatology, assessment of the defect data, etc., etc. So just to finalize, I think we are more or less in time. And regarding to the data life cycle, it's important to use the data. When you are starting to use the data, many questions arise. So contact with the person, me, other person that can help you to solve this question, this issue. Learn about the data, about the use of this data, and use again the data to take more profits. Okay. In this regard, there is another important question. Usually, this kind of platform, I think, is really important also to improve the data. This kind of platform provide questionnaire, and I mean they make surveys for the user, etc., where they get the information of the user about the data, and they use that to improve the data, the explanation about the data, the availability according to the preference of the user. So this part is also important to take more profit from this kind of data. So this is all. I don't know if you have time for some question. You should remember you should do the quiz. We are like 4 questions, so very briefly about the information that you can you have seen the slide on the speech. So let me know if you have some. This is my email. You can contact in case you are interested in some specific or thematic data, etc., or data set. You can contact, and I will try to help you on the use of the data. Okay, I would recommend to go there to the cements and start to play with that and register, because we will use it later. Okay, thanks for your attention. I don't know if you have some question.